Rayleigh-Ritz, Galerkin. These names alone and combinations refer to distinct but related computational techniques. So, what are these techniques? And who did what? This webinar summarizes my investigation of these names and techniques, and then made them concrete by implementation in Maple. And throughout this study, I never ceased hearing the syncopated rhythm of the song Puttin on the Ritz. The song, well, these are the words of the 1946 version. It's actually a 1927 song written by Irving Berlin. It's been recorded many times. There's a 1930 movie that has it in it. But the really interesting movie is the movie Blue Skies, 1946, where Fred Astaire sings and dances to this thing, and the rhythm is just incredible. It's haunting. So look for this version, 1946, Blue Skies. Just Google and enjoy the 4 minutes of watching Fred Astaire sing and dance to this. Just amazing. Let's have a quick roadmap through what we're going to look at. Here are the names: Rayleigh-Ritz, Galerkin, and Ritz-Galerkin. And what are the techniques associated with these names? Well, you have this thing called the Rayleigh Quotient. Then you have Rayleigh's principle for finding the eigenvalues of a Hermitian matrix. You even have Courant gets into the act with a min-max principle to approximate the eigenvalues of a Hermitian matrix. What did Ritz himself contribute here? A direct method in the variational calculus, and with it you can approximate solutions of self-adjoint boundary value problems. Rayleigh-Ritz, approximate solution of Sturm-Liouville eigenvalue boundary value problems. So you can see the mix of what Rayleigh contributed and what Ritz contributed. Galerkin, extension of the Ritz technique, the more general boundary value problems. And also you can use it to approximate solution of eigenvalue problems for ODEs. What references did I use for this? Applied Linear Algebra by Noble and Daniel. It's a linear algebra book. Boundary and Eigenvalue Problems in Mathematical Physics, Hans Sagan's book, 1961, and the Kantorovich and Krylov book, Approximate Methods of Higher Analysis, the 64 translation by Benster. The Sagan book, I had used it as an undergraduate in college. Thought it was a good book then, but when I went back to it to look up this material, I discovered I didn't like it. I didn't think it was well written. But it did have the reference to this book, Kantorovich and Krylov. I went to the internet, dug up a copy, bought the translation, and those are the books that I use for this project. Recently I ran across a note on the text by Kantorovich and Krylov. It appeared in Math Monthly, and here's the author, and he points out that something about two mathematicians winning the Nobel Prize in economics. Somebody let me know that there's another mathematician, a Reinhard Selten, who also shared the Nobel Prize in economics. But I'm just quoting what this particular John Boyd had to say. But essentially what he's talking about is the book and the techniques that were used in that book, that they were all by hand. That's what this word means, medical term. And now with computer algebra systems, so much additional insight can be obtained with fewer mistakes. So I was just surprised when I ran across this as I was digging through all of this material. Let's get on with the meat of this webinar, starting with the Rayleigh quotient. Okay, what do we mean by the Rayleigh quotient? It's given Hermitian matrix A, you look at the bilinear form divided by the length of the vector in the bilinear form, and you have to make the restriction the vector is not the zero vector. If you make this simple transformation, you can replace this formulation of the Rayleigh quotient with just the bilinear form restricted to norm 1 vectors. The Rayleigh quotient is important here because there's a connection between it and extremization, and the connection is eigenpairs. Let's take a look at what we're saying here. Here's the quadratic form. That's the Rayleigh quotient. A is a Hermitian matrix, and I'm making this claim, which I will substantiate down here. The gradient of this function is 2ax. Just hold that, believe that for a second. Okay, we're going to take the extrema over the constraint norm squared equals 1. Using Lagrange multiplier method, you have to then write the equation grad f equals lambda grad g. Well, we have a statement about grad f. Grad g, that should be pretty clear. This is a sum of squares. You'll have a 2, and you have the differentiation of each of the variables, 2 lambda x on the right side. So we have this equation. From here, 2ax, 2 lambda x from here. That's the eigenvalue equation. Ax equals lambda x. So the extrema of this quadratic form are the eigenpairs lambda hat, x hat. If you put x hat back into the function, do a little arithmetic, you get lambda hat. So if you get the lambda, you can if you can get the x, you can get the lambda. The extrema of this quadratic form are eigenvalues and are obtained at the eigenvectors. So that's the importance of the Rayleigh quotient. So now let's prove this contention here, grad f. Okay, so here's A. I look at the 3x3 case. Remember, it's Hermitian, so you have the symmetry. And here's x. So what does x dot ax look like? Well, here's x dot ax. Here are the columns of A. You take linear combinations with the coefficients being x, y, z. That's what matrix multiplication is all about. Now, move the dot product inside the parentheses. So you have dot here, and dot here. And here you have an x, here you have a y, and then here you have a z. Now start taking the dot products. You see the x squared a11 term here. Then you will have an xy a12. That's this term. And then you'll have an xz a13 over here. Similarly for these other two dot products. Now gather the terms. Put the squares here, x squared, y squared, z squared, and the mixed terms here. Now you can take the gradient. So when you take the gradient, what's going to happen? You differentiate first with respect to x. So you're going to get a 2 a11 x. So here's the 2 out front, a11 x. You're going to pick up an x here, so it's 2 a12 y. And from here, you'll get 2 a13 z. Then you differentiate with respect to y, so you get this term first here, a22y from here. Then when you differentiate this term, you pick up the a12x, and when you differentiate this term, you get a23z, so forth. When you look at this, you realize you have x's here, y's here, z's here. Pull that out. That's the x here. These are the columns, a11, a12, a13, and so forth. This is ax. And so the contention is just a bit of simple linear algebra. So Rayleigh's principle. Let A be Hermitian. It has eigenvalues that are real. You have p eigenvalues, and you have p eigenvectors, which you can make orthonormal. I mean, that's a fact about Hermitian matrices. Now, line them up in size order. Let LK be the span of the first k eigenvectors, and LK perp be the orthogonal complement. So that means that LK perp contains the rest of the eigenvectors. Okay, so LK has the first k, the perp has the rest of them. And then you do the same thing with the upper k. Take RK is the span of the upper bunch. The perp then contains the lower bunch. And here's the principle. If you minimize the Rayleigh quotient over the perp of L, so LK perp, you will get the next eigenvalue, and the corresponding eigenvector will be the next eigenvector, because that's what's in that bunch. And similarly, if you take the max over the perp of the right-hand bunch, the big bunch at the top end, okay, you get the next smaller one because that's what's in the perp. It's easy to implement this in Maple. You minimize subject to a constraint, maximize subject to a constraint. So I'll show you in a minute here an example of how this can be easily done in Maple to test this out to see if this stuff really makes sense. Okay, an example. How did I do that in Maple? Load the student linear algebra package. Define the variables. I have a 5x5. So I use variables x, y, z, w, u. X is the vector with whose components are x, y, z, w, u. And since I want to make use of this Lagrange multipliers command from the student multivariate calculus package, without conflicting with some of the other packages in Maple, I aliased LM for Lagrange multipliers. Okay, so here's the matrix. Where did I get this matrix from? I found it by rummaging in the internet for an algorithm that produced a symmetric matrix with prescribed eigenvalues. Prescribed eigenvalues that I took were 2, 3, 4, 5, 6. Here are the corresponding orthonormal eigenvectors, easily done in Maple. You find the eigenvectors, you can Gram-Schmidt them. Bilinear form, x.ax, I call it f. Okay, so now I want to do extremization. Okay, so Lagrange multipliers apply to this bilinear form. This is the constraint. Norm equals 1, and you have to write as norm minus 1 for this particular command. And the output equals details gives you all of the solutions. It gives you the values of the variables, the Lagrange multipliers, and the value of the function f. So you have to search through that to pick out where the eigenvalue is showing up, and that's what this right-hand side does. It finds that equation, lambda equals, takes the right-hand side of that, that's the eigenvalue, and I make a sequence for each of the solutions, and so you see I have recovered 2, 3, 4, 5, 6. Now, if I minimize over L1 perp, so L1 is the leftmost eigenvector span of the leftmost eigenvector. So the perp is the stuff to the right, so it's the next one up. So when I put in the constraint that x and the first eigenvector are orthogonal, that puts me in the perp, okay? And I do this minimization, I find that the lambda is 3, and the corresponding eigenvector that I get is, well, it turns out to be the negative, because there are 2 of them, right? So it's just a question of hunting through and getting the right one oriented in the correct direction, which I didn't bother to do. Okay, so I tried it. Let's go up a notch. So let's look at L2 perp. So I've got 2 eigenvectors. Perp has the next bunch of them, so V3 is in there, and I will pick up the next lambda. There is the next lambda. I do this with L3, so the perp has L4 in it, and I pick up lambda equals 5. Do it one more time, I pick up lambda equals 6. I also want maximize, so I started with the upper bunch. I take the biggest one. Here's the orthogonality condition, and I get the next lowest eigenvalue, which is 5. Then I do it with 2 of them, and I get 4. Then I do it with 3 of them, and I get lambda equals 3. And I do it with 4 of them, and I get down to the very first one. I get lambda equals 2. The min-max principle. Now, I found this in the Nobles and Daniel book, and I believe they attribute it to Courant. It looks a lot like what we just did with the Rayleigh principle, but it's a generalization. Okay, so we have this Hermitian matrix. You line up the eigenvalues in size order, and it has orthonormal eigenvectors. Rayleigh quotient. Now, look at this subspace, CR. It's a subspace spanned by R independent vectors. Might have eigenvectors in there, might not. Okay? R independent vectors. And here is the orthogonal complement of those vectors. Now, if you maximize over the perp, and if these were the rightmost eigenvectors, then you would be finding the next smaller eigenvalue. But these are not necessarily eigenvectors. So you minimize, you get the smallest number of all possible numbers you can generate by taking all possible subspaces of dimension R. And that will approach and become that next smallest eigenvalue. So consequently, you're finding an upper bound, you're approximating it because you can only take a finite number of these subspaces, so you're getting an upper bound for those lambdas. Alternatively, if you would minimize over that collection, that perp, okay, you'd be finding the next bigger one. So you take the max, and that becomes a lower bound for the next eigenvalue, the next bigger one. So I looked at this and said, oh, how would you do this? Is this true? Does this work? It turns out you can implement this easily in Maple, and I will do that next. I will show you an implementation in Maple. So let's look at an implementation of this min-max principle. I found out I had to make myself a little chart here of what I was computing. If you do min of the max, then you're going down the ladder. You're going to be finding successively smaller eigenvalues. If you do max of the min, then you're going up the chain and you're finding successively larger eigenvalues. So let's start with r equals 1. So we have a one-dimensional subspace, and we search in the perp. Okay, what we're going to find is an upper bound for this eigenvalue. And a lower bound for this eigenvalue. So what is the computation here? We need to have some vectors little c, k. So we need one to start with. I just did a random vector. Okay. I'm searching over vectors of length 1, and I'm looking in the perp, the orthogonal complement of this vector little c1, I call it uppercase c1 to be consistent, do the extremization here, Lagrange multipliers, and since I'm looking for small and big, I didn't want to do the computation twice, so I just searched through, and whenever I found a small one, I put it in one place, and whenever I found the biggest one, I put it in the other place. Then I took the smallest of those and the biggest of those, and here's what the numbers turn out to be. Upper bound pushing down on 5 and pushing up against 3. All right, so I just said, can I keep going? So now I have my CR now has dimension 2, so I have 2 of these vectors. Here, this creates the perp of those 2 vectors. Do the same thing, and I'm pushing down against lambda equals 4 and up against lambda equals 4 because that's in the middle. These are the 2 bounds. I tried it with 3. I have 3 vectors, 3 orthogonality conditions, the same computation, pushing down against 3 and up against 5. Did it one more time. Now you'll notice that here and here I had to do it, repeat the experiment more times to get accuracy, a reasonable accuracy. So instead of 20, I had to go to 50 different sets, but the process is the same. And here I'm pushing down on 2 and up against 6. Okay, so where is this going? Ultimately, you're thinking in terms of eigenvalue problems for differential equations. And you look at this linear algebra stuff and you say to yourself, can you tackle the eigenvalue problem in differential equations with any of this structure, any of these concepts that you just looked at in linear algebra? And it turns out that you can, but the path is through variational calculus. So in the calculus of variation, you're doing extremization. What are you extremizing? A functional, typically of something like this, a function of x, y, and y prime, and y satisfies some boundary conditions. The indirect condition, indirect method, is the Euler-Lagrange equation, which is you take the partial of f with respect to y and you subtract x derivative of the partial with respect to y prime. The isoperimetric problem is extremize this same functional, but add on this integral constraint. So this function in the constraint is similar to this function here. It's a function of x, y, and y prime, but it's equal to some constant. So think of this as you want to maximize area, and this is the perimeter. So you fix the perimeter, what's the maximum area? And we all know that's a circle. Okay, so how do you solve that problem? You write a new functional whose integrand is f minus lambda g. So you introduce this Lagrange multiplier, f minus lambda g. And you apply the Euler-Lagrange equation to it. So it's big F sub y minus derivative of big F sub y prime. Okay, so that's an extremization in the variational calculus. All right, I've just shown two optimization problems in the variational calculus. Now I want to show two boundary value problems. Then I have to connect them. All right, so with some conditions on the coefficients, here is the self-adjoint boundary value problem, and here is the Sturm-Liouville eigenvalue problem. All right, so py prime prime qy plus g equals 0. You can write it in an operator form, so it looks like Ly equals minus g. The Sturm-Liouville eigenvalue problem has that same structure, except you now have a term lambda. You could even have a weighting function wy. You can also construct that in an operator form, and it now looks like Ly equals lambda y, and it looks just like your eigenvalue problem for linear algebra. And ultimately, we're looking to obtain approximate solutions, the way we've found approximate solutions to the eigenvalues. Here you will see the name Ritz. You will also see the name Galerkin. Here you will see Ritz-Galerkin or Rayleigh-Ritz. You need to take a look at some of these examples. Can we cast these boundary value problems as optimization problems? Well, let's look first at the self-adjoint boundary value problem. This is the self-adjoint boundary value problem. This is the equation for self-adjoint boundary value problem. Consider this functional where f is p y prime squared minus qy squared minus 2gy. Take the Euler-Lagrange equation of that functional. What do? You differentiate with respect to y. So you pick out minus 2qy minus 2g. It's this term. Then you take the x derivative of the derivative with respect to y prime. And y prime sits here, so it's 2p y prime. So you're taking the x derivative of 2p y prime. Now, get rid of the minus signs, get rid of the 2's, and you see py prime prime. You have qy, and you have g. So this self-adjoint boundary value problem is related to finding the extrema of this functional. So we are linking the self-adjoint boundary value problem to an optimization problem in the calculus of variations. Can we do the same thing for the Sturm-Liouville eigenvalue problem? This is the Sturm-Liouville differential equation when it's an eigenvalue problem. Well, if we minimize this functional subject to this constraint, we know how to do that. We write a new functional. We take this integrand and we subtract lambda times this integrand. And we apply the Euler-Lagrange equation to this new functional, capital F. So we need the derivative of this with respect to y. So you're going to get a minus 2qy from this term and a minus 2 lambda wy from this term. Then we need to take the x derivative, put a minus sign, of the derivative of this functional with respect to y prime. And so the only place y prime appears is here. So you have 2p y prime. You're taking the x derivative and you're going to do a subtraction. So when you put it all together, which is what we're doing here, you have a minus 2 here, here, and here, which you can factor out. You have py prime prime. You have qy, that's this term, and you have lambda wy, that's this term, and if you factor out the y from these two terms, you have the Sturm-Liouville eigenvalue problem. So this differential equation and this problem in the calculus of variations are equivalent. You can go back and forth between those two. Let's connect the names Ritz, Galerkin, and the idea of the self-adjoint boundary value problem, not the eigenvalue problem, just the boundary value problem. And what we have here is the differential equation, and we've seen that an equivalent problem is extremizing this particular functional. So we have this differential equation. We want to solve it by converting it over to this minimization or extremization problem, and we have two techniques. We have finite difference technique. This is the kind of thing Euler would do. Discretize the x interval. Replace the integral with a sum. So in the integrand, wherever you need an x, you put an xk. The unknowns are the corresponding values of the function y at xk. And for the derivative, do something simple like a forward difference. This is going to produce a function of the yks. This is an approximation to that integral. You want to minimize or extremize that integral. So take partial derivatives of this function with respect to yk. You have a set of equations to solve for the yk. On the other hand, Ritz came up with this approach. Approximate the solution as a linear combination of some basis type functions. So little phi k's are basis functions, ck are the coefficients of this linear sum, and tack on a function phi 0. Let phi 0 satisfy the boundary conditions. Let these other phi k's satisfy 0 null boundary conditions. So the boundary conditions are handled by, the endpoint values are handled by this phi 0. Well, put this function into the integral, carry out the integration. What are you going to end up with? You're going to end up with something that just these ck's. So you're minimizing or extremizing. So you take partial derivatives of this function with respect to the ck's, set that equal to 0. You get a set of equations for the ck's, and you end up with a function phi that's an approximation to the solution of this differential equation. So we see what Ritz did. You want to solve this differential equation, cast it as this functional, solve the problem in this form, and then you get an approximate solution by this Ritz technique. Now let's follow that out and see how it ends up getting Galerkin into the picture. Let's look at this function j. What is it going to look like? Well, for this differential equation, you're going to form this functional. I've used an overdot to replace the prime because squaring a prime or putting a derivative prime on a subscripted variable just does not look right in Maple. So the over dot is the prime just so that it looks better on the screen. So this is the functional that replaces this differential equation when you use this variational calculus approach to solving the differential equation. You're going to differentiate with respect to these constants ck. So think about phi prime. The primes will be on these little phi's. So when you differentiate with respect to the c, you have these primes, and you square that, you're going to get 2. There's the p. You will get the expression, is phi dot, but you will also pull out the phi prime here. Now this doesn't have any derivatives, but it's squared. So you're going to get 2q, you'll get the phi, and then you'll pull out the phi k because you're differentiating with respect to c. And here you will just get the phi k. So this is what you set equal to 0. Well, you got 2's. You can take them out. Now look at this term here. It's got a phi dot. These two have phi's. And so we want to integrate by parts to shift derivative from here to here. So everybody will be a phi, a little phi. Then you can factor that. Okay? So integration by parts, you're shifting the derivative onto this product. So that's what this results in. These two terms don't change. Now, over here in this boundary term, remember the phi k's have been chosen so that they vanish at the endpoints. So this boundary term is gone. So this integral looks like this. P phi prime prime q phi g. That's L. That's L on this Ritz approximation multiplied by the basis function phi k set equal to 0. That gives you a set of equations. So what did Galerkin say? He said, look, this is an orthogonality condition. You are making the residual for this approximate Ritz function orthogonal to these phi k's. Make the residual orthogonal to something else, something more amenable. So that's what the Galerkin extension is. Choose, instead of phi k in these equations, a set of orthogonal functions, and see if you can get the residual closer to 0 in this integration sense. Okay, let's do an example. And I call this an example of Galerkin for a boundary value problem. Here's the differential equation. Now, notice it is not self-adjoint. This is not formally self-adjoint. And that's another aspect of Galerkin's extension. Ritz had to have a self-adjoint differential equation, formally self-adjoint differential equation, in order to cast it into variational form, in order to use his approximation technique. But Galerkin said neither the little phi k's nor the fact that the equation is not self-adjoint matters. So I want to check that out. So here's a differential equation, some boundary conditions. This equation has an exact solution because I want to see how good a job I did. Here are my three little phi k's. These two are orthonormal. Or they're at least orthogonal. So here's my approximating function. X plus a sine pi x b sine 2 pi x. I need the residual. So I take this function and I put it into the differential equation and I get a residual. Well, it's clearly not 0. If it had been 0, I would have guessed at the solution to the problem, but it's not 0. So I want to make this as close to 0 as I can. I will integrate against the phi 1 and phi 2. I get these two equations. They contain a and b. I solve for a and b. I put those a and b back into this Ritz or Galerkin approximation, and I get y approximate. And of course, you want to compare, and here's a graphical comparison. So this stuff works. It's not crazy. This stuff actually works. Okay, let's see if this stuff works for the eigenvalue problem. I'm going to take a problem for which I can get an exact solution, or as close to an exact solution as I can. So the coefficient p will be something that's non-routine, root of 1 plus x. So py prime prime, and p is this root of 1 plus x plus lambda y. So it's an eigenvalue problem. Endpoint conditions. I can get an exact solution to the differential equation. Just the differential equation, no boundary conditions. I will have to get apply the boundary conditions myself. So I apply these two conditions, and that gives me two equations. They're homogeneous, and the equations are for C1 and C2. So I put those equations into a matrix format. So the column vector over here is C1, C2, and that's equal to 0, 0. This determinant has to be 0 for a non-zero solution to these coefficients to exist. So I take the determinant and I set this equal to 0, and I find the lambdas that make this determinant be 0. And I find the simplest way to do that is to use the roots command in the student calculus 1 package, and I calculate these first 5 eigenvalues. And I want to get at least one eigenfunction, because I want to see if this Ritz-Galerkin stuff produces an eigenfunction. So in order to do that, I take one of the boundary conditions. I substitute this first eigenvalue. I get this equation from the boundary condition. So I can solve for one of these coefficients in terms of the other. I solve for C2. And I put that back in here. You notice it's C1 here and C1 here, which is what you get when you do an eigenvalue problem. You get to within a multiple. I call that Y1. Now, I'm going to try to determine a reasonable value for this constant C1 by normalizing using the L2 norm. So square, integrate, solve for C1, put that back in, and I call that Y sub 1. So there is this normalized first eigenfunction. And here is its graph. Now notice how high up the graph goes. 0.0, 0.8. Now, there is a way to check this numerically in Maple. If you use dsolve, there's the differential equation. There are the two boundary conditions, but you throw in one other condition, something. Y prime at 0 is 1. You do a numeric solution. If you're lucky, you will get back a solution that indicates what the eigenvalue is, and that eigenvalue that Maple has come up with, 1.63709. Go back over here. Can you remember that long enough? Where did that happen? Here, 1.63709. Then it's 8827 there. 88. So we have about 6 places, 7 places accuracy. But look at this graph of the eigenfunction that Maple has computed numerically. It doesn't go up as high. So I asked the programmer who put this technique into Maple if there's any attempt for any kind of normalization, and the answer is no. There is no attempt to do any kind of normalization. What you get is what you get. So our normalization that brought the height up to 0.8, and whatever Maple did here to compute this solution, no connection. Okay, so we have this problem that we can use to compare against. We have almost an exact solution. Let's try this Ritz-Galerkin stuff. I need some little phi k's, some basis functions. So phi 1 through phi 5, they satisfy the 0 endpoint conditions, right? At 0 and at 3, go to 0. These are not orthogonal functions. I did all the integrals. This matrix of integrals is not diagonal, so these are not orthogonal functions. However, I constructed them to have this interlocking 0 property, which is a property that solutions to the Sturm-Liouville Eigenvalue Problem have. So I just thought it might be helpful to do that. I needed some functions, so I picked those. Okay, so we need these Galerkin-Ritz type equations where you have the residual on the approximation integrated against something. So here is my approximate solution, and I've tried 1 term, 2 terms, 3 terms, 4 terms, 5 terms. So I actually have 5 of these approximating functions because I want to see how far up you have to go to get a decent answer. So with 1 term, this is going to generate the residual. Now I'll integrate it against little phi 1. This is the equation. I'll set that equal to 0. You don't want A1 to be 0, so you have to calculate the lambda that makes this equal to 0, and it turns out to be 1.7. So that's an approximation to lambda 1. So let's do 2 terms, phi 2, big phi 2, which has 2 terms. So this is going to give us 2 equations. They will be homogeneous, so we have to do this matrix determinant trick. So we do the matrix determinant trick. The determinant is now quadratic in lambda, and we get 2 values for lambda. This approximation is closer, 1.6, it's closer, and this is an approximation to the second eigenvalue. Let's try 3. So you're going to get 3 equations. This will again be subjected to this matrix determinant trick. The determinant is now cubic in lambda, so you're going to get 3 roots. This approximation to phi to lambda 1 is closer. This is an approximation to lambda 2. This is an approximation to lambda 3. I want to construct an eigenfunction so we can compare it to the eigenfunction that we got earlier. When we took 3 terms in our Ritz approximation, we got a much better approximation to the first eigenvalue. So let's construct a corresponding eigenfunction. Now, lambda is not known exactly. You can't put that back into the differential equation and expect to get the eigenfunction. If you put it into the matrix M, you will not get a non-zero solution because the lambda is not the exactly right number. So this technique seems to work. Put that lambda into two of the three equations. Solve for two constants in terms of the third. And that's what I did here. Put that into phi 3. You have the solution given in terms of this multiplicative constant A3. Let's normalize it the same way that we normalized earlier. Use L2 normalization. And this is a graph of that eigenfunction, approximate eigenfunction. And you notice that it goes up close to 0.8. Now here's an alternate view of these calculations. And this would be something that would have to be done if you didn't have a tool like Maple to do these computations. You'd be working this stuff out more by hand, trying to see some kind of structure that you can take advantage of to do by hand calculations. Okay, so L phi n, that's the residual. You integrate it against something, and I'm integrating it against the phi k's that I used when I constructed the phi n to make the residual orthogonal to as many functions as possible, driving it as close to the zero vector function space as we can. So this is what L phi n looks like. There's a derivative on this term. It's multiplied by phi k. So I put the phi k over here so you can see this term. And I want to shift this derivative off this product and onto the phi k. So I used integration by parts. Minus sign here, I'm setting this stuff equal to 0, so I want this positive, this negative. And so I'm looking at this term. This is a sum of coefficients a1 through an and functions phi 1 through phi n, but they're differentiated here, differentiated here. Here, you have the same products, but not differentiated. No derivatives here, derivatives on both terms here. So define these numbers. Alpha ki and beta ik. They are the integrals of the phi's, the little phi's here, and the little phi's here. The coefficients are in this vector C. So these numbers you put into a matrix. These numbers you put into a matrix. What you can then write from this equation is AC minus lambda BC equals 0, which is a generalized eigenvalue problem. And so if you in Kantorovich and Krylov, they now launch into a discussion of how to solve this generalized eigenvalue problem. Well, people can solve the generalized eigenvalue problem. But if you want to see this stuff in some detail, to see that these numbers are what we say, I've worked out an example here where n equals 2, so you can see what all of these terms look like, that these alphas and beta terms do indeed lead to this generalized eigenvalue problem. Well, that's easy enough to implement in Maple because Maple will do the integrations and it will form the matrix A. We'll do the integration, form the matrix B. It will calculate the eigenvalues for the generalized eigenvalue problem. And I have assembled the calculations into this tableau. And what I have done is I've incremented the number of basis functions that I've used. I've used 1, then I did 2, then I did 3, then I did 4. Okay, so this is what happens if you use one basis function. This is what happens if you use two basis functions. This is what happens 3, 4, and 5. So this is an approximate value for the first eigenvalue. Second eigenvalue. A better approximation for that first eigenvalue. Better, better, better. So this is the one that we computed, let's call it exactly. So these approximations get better and better to the first eigenvalue as you increase the number of basis functions. Okay, this is now for the second eigenvalue. The approximations get better and better. This is the exact one. Third eigenvalue. Approximation, approximation, approximation. This is the exact one. So now you see, not so good. 30 here, 26 here, 63 here, 41 here. So you need to take more and more basis functions for this process to converge. Now let's mix the ideas of Rayleigh and Ritz and see what we come up with. Okay, we want to solve this Sturm-Liouville eigenvalue problem. So we replace it, according to Ritz, with a variational problem. So you can either put the pieces together this way and optimize this functional, or you can pull it apart and separate them into these two components, minimize or optimize this functional subject to this constraint. So if you make this Ritz approximation, phi k, and you put it in here, you will get a function of the coefficients, the a1 through ak, that you are trying to extremize, but it's subject to this constraint, so that produces a different function of the a1 through ak equal to 1. So this looks a lot like get the extreme values of bilinear form subject to a constraint. So it looks like what Rayleigh was playing with earlier on. Oh, of course, we need to test this out. Let's see how this stuff works. Okay, so objective function. This is the objective function when we take one basis function, and this is the constraint when we take one basis function. We're going to use Lagrange multipliers to get extreme values of this subject to this equal to 1. So this is how you put it in. Bring everything to the left, and you don't put an equation, you drop off the equal 0. We're solving for this first coefficient, and then we have to rummage through the stuff that this output equals detail produces, and this is the value of the Lagrange multiplier for this problem. So it's an approximation to that first eigenvalue. Now this is what we do when we have two. We use two basis functions. So this is 5, 2. We do the same calculations. This is the constraint. We're looking for two unknowns. Again, sort and pull out the lambdas. So now this is another approximation to lambda 1, which is better than this one. And here's an approximation to lambda 2. This is what happens when you have three basis functions you get three numbers here. This is approximation to the first eigenvalue, second, third. If you take 4, you get 4 here, and if you take 5, you get 5 here, and if you put them into a tableau, it will look like this, and you'll notice that the eigenfunction is approximated by phi 5. That's the solution of the differential equation, right? And you'll notice it has the right shape, and you see the height 0.8. And the tableau is the same tableau we got earlier. These are the approximate values of phi 1 getting better and better, or lambda 1 getting better and better, and this is what we had computed, quote, exactly. Similarly for phi 2, so forth. So this has been a journey through these names and techniques. You'll find the literature is pretty muddled about who did what and what names to call stuff. This is my understanding of how these ideas play out.